are not particularly realistic. Distributed charges are realistic. And so when we talk about the difference between point charges and distributed charges, it's important to know why I would bring these up. Point charges versus distributions. And let me help you with what I mean by this. Imagine I have a line in space. And affixed to this line, starting at the origin, I place charges in a regular and repeating pattern. Each charge being the same value, Q. And they go off in each direction forever. And they're all a distance s apart. And let's say directly above the origin, I bring another charge, Q. In this problem, can we agree that Q is going to experience a downwards force, a force in the negative y direction, so to speak? We know that. Based on the symmetry of the question, the net force on Q is very likely to be this way. I don't have to be super involved to understand that, because for every particle over here is a particle over here. So although there are some off-axis forces, for every off-axis force, there's one that balances, so that there's no forces that are in the x direction. The net force is all in the y direction. Can you guys see that okay? Do I have to draw more arrows by going to the next charge and saying, okay, there's one this way, but there's also one this way? So the x direction forces cancel out, but all the y direction forces add together. Okay so far? Now you guys who are taking calculus right now, and especially if you're in AB, you're doing all that work on limits right now. I see a problem that has limits in it. I should imagine. There's a pair of charges right here, right? This is a pair of charges. I can easily write out what the size of that force should be from that pair of charges. I mean, it's going to be Q squared K over A squared. Correct? But what if instead I'm interested in going to the next charge to the right and left? Meaning I look at that pair, right? I know there's another pair on the other side that'll have the same size force. So if I focus on this pair for right now, I know that I'm going to be doing two of the charges at once, right? Because there's a force in this direction. And there is a symmetrical force from this charge in the other direction. Are we okay so far? I'm going to focus on just this force, though. And whatever I get for my response, I'm going to double it, because I know there's one on the other side. Everybody okay with that? So what does this force look like? You do it. Do it right now. Give me an expression for that force. Not hard. I'm not asking for any trig. Just asking you to find me an expression for that force. I want to know that you're paying attention, and I'm going to come by and you're going to point at it and say, this is what I got. I'll give you 60 seconds to do so.
Can we use data?
Nope. You won't need it. You might need to use the Pythagorean theorem in your answer.
Let me talk to him.
Don't have time. I don't have time to go around and look at yours either. This is what it has to be. All right, still 2 q's, so that's q squared. The separation distance is the square root of a squared plus s squared, and then I square it, put it in the denominator. So this has got to be it, right? And there's 2 of them, but wait, I don't want all of that. I want just the part that's this way. So I do need to scale it by the cosine of an angle I can't use. Right, the cosine of this angle. So I have to scale it. So the cosine of that angle, I'll give it a name theta, but the cosine is a over the square root of a squared plus s squared. Do you see that okay? Oh, we've done this problem already once, by the way. I'm just bringing it back up. And the bell's going to ring, so I'd like to hustle a little bit. And how many contributions to this force are there? 2. Now, before you walk away, do you understand that if I want to go to the next one, it's all the same, except s is now 2s? And if I want to go to this one, it's all the same, except s becomes 3s, and this one's going to be
4s.
Do you see a problem that has a limit as n times s goes to infinity? Right? Because there's that many particles. You guys have done limit problems. This is like this. It's a limit problem. Now, I don't want to talk about this problem. What I want to talk about is what happens when the whole bar is just one continuous charge. How do we do that? A charged bar in space. That's the real problem we have to do. And that's new math for you guys. This was old math, simple trig and stuff. This is going to be new math. All right, goodbye.